Section 10.7.2 Arithmetic Coding. Arithmetic coding, pronounced arithmetic, is a text compression method that I invented in the 1970s. Arithmetic stream coding using fixed precision registers. It is based on a clever idea from Peter Elias of MIT. Elias's idea was to encode every character string as a fraction. Imagine all the possible fractions from 0 through 0.999. The ellipsis ... means that this fraction ends with an infinite sequence of nines. Now divide this range up according to the first character of the string. For simplicity, let's suppose there are 25 characters in the alphabet, like a Polybius square alphabet. Each letter will get 1/25 of the full range. Those strings starting with A get the first 1/25 or 4% of the range, namely 0 to 0.04. Strings starting with B get the next 1/25 of the range, namely 0.04 to 0.08. Strings starting with Z get the last 1/25 of the range, 0.96 to 0.999. I am giving this example using decimal notation to make it easier to read. In a computer, binary fractions would be used. For the second character, you divide this range again. Strings starting with AA would be in the range 0 to 0.0016. Strings starting with AB would be in the range 0.0016 to 0.0032. Strings starting with BA would be in the range 0.0400 to 0.0416, and so forth. Strings starting with ZZ would get the range from 0.9984 to 0.9999. To visualize this, let's use a miniature 5-letter alphabet, with A being 0 to 0.2, B from 0.2 to 0.4, C from 0.4 to 0.6, D from 0.6 to 0.8, and E from 0.8 to 0.999. Using this alphabet, let's encode the word bed. Bed could be encoded as any fraction f with 0.384 less than or equal to f less than 0.392. As more characters are added, this interval will continue to shrink. That's the concept. However, this encoding of strings as fractions does not give any compression. One more idea is needed to get compression. Instead of giving each letter of the alphabet the same fraction of the range, make the fraction proportional to the frequency of that letter. A would get 8.12%, B would get 1.49%, through Z, which would get 0.07%. The range for A would be 0 to 0.0812. The range for B would be 0.0812 to 0.0961. The range for Z would be 0.9993 to 0.9999. In theory, this would give optimal compression based on the frequencies of the individual letters. Unfortunately, there is a practical problem. The method produces fractions that potentially require thousands or even millions of digits. How can such fractions be represented in the computer? How can you perform arithmetic on them? So the method was great in theory, but seemingly infeasible in practice. It appeared to require fractions of unbounded precision. The time needed to add and multiply long fractions, whether decimal or binary, increases with their length, so even if there were a good way to represent these fractions, the method would be impractically slow. The solution I found was to use a moving window where all of the arithmetic would be done. That lets you use ordinary 32-bit integers. No floating-point arithmetic was required. To keep the integers within the 32-bit size, the letter frequencies were approximated by 15-bit integers, that is, by a fraction of the form n over 2 to the power 15, or n over 32768. For example, the frequency of the letter A is 8.12%. This can be expressed as 2660 over 32768, or 665 over 8192. This approximation was found to cause no detectable reduction in the degree of compression. Here is a decimal example to show how a letter is encoded and how the moving window works. Suppose the first few characters have been encoded and the range is now 0.784627 to 0.784632. The first four digits for the start and end of the range are the same, namely 0.7846. These four digits would be output, and the window would be moved 4 digits to the right to show the range 0.2700 to 0.3200. The width of this range is 0.0500. Suppose the next character in the message has a frequency of 0.0300 and its range is 0.4050 to 0.4350. This character gets encoded by selecting that fraction of the current range, 0.2700 to 0.3200. Its width is 0.0500 times 0.0300, which is 0.0015. It will run from 0.2700 plus 0.0500 times 0.4050 to 0.2700 plus 0.0500 times 0.4350, which is 0.29025 to 0.29175. Notice that the width of this range is 0.0015 as expected. Since the start and end of this range both begin with the digits 0.29, these digits can be output. The digits that have been output are now 784629. The window can now be moved 2 more digits to the right to make the current range 0.0250 to 0.1750. Arithmetic coding is ideally suited for encryption because there are no longer discrete codes for each letter or letter combination. There are no boundaries where the bit stream can be broken into separate codes. Instead, the code for each letter influences how all subsequent letters are represented. Now that we understand how the arithmetic coding method works, the next step is to see how to use it for encryption. We do not want to change the percentage of the range allotted to each character because that would lose the compression. Instead, we can change the order of the characters so that the range for each character falls in an unpredictable part of the full range. That is, unpredictable for Emily. For example, using just the letters A, B, C, D, E, the ranges might be. These intervals can be used to encode the letters of the message. Let's call this method arithmetic encipherment. Since Emily does not know either the starting point or the ending point of any of the ranges, there is no opening for an attack. It is true that Emily knows that the first range starts at 0 and that the last range ends at 0.999, but Emily does not know which characters these ranges represent. There is one difficulty with arithmetic coding that has not been discussed yet. Using the normal alphabet, Riva does not know where the message ends. The same code that stands for rotund could also stand for rotunda, R-O-T-U-N-D-A-A, R-O-T-U-N-D-A-A-A, ad infinitum, assuming that the range for A begins at 0. With conventional arithmetic coding, this problem can be solved by using various ways of encoding the length of the message and appending this length code to the ciphertext, or by adding a special end-of-message character to the alphabet. This was not discussed earlier because it is not needed for arithmetic encipherment. With arithmetic encipherment, all you need to do is assign a rare character, or any character that is seldom found at the end of a message, to the first range, that is, to the range starting at 0.0000. Then when Reaver sees ROTUNDVVV or ROTUND ###, it is obvious where the message ends. As described here, arithmetic encipherment is rated 5 using a 26-letter alphabet, or 6 using a 256-character alphabet. All the usual tricks can be used here: nulls, homophones and bigrams. Using nulls would reduce or destroy the compression, so I do not recommend that. Using homophones has the effect of splitting the range for a letter into 2 or more separate ranges. This makes the ranges for the letters more even, which is equivalent to flattening the letter frequencies. This can improve the security without affecting the degree of compression. Using bigrams or even trigrams can sometimes increase the level of compression while improving the security. Using homophones and bigrams, arithmetic encipherment is rated 8. Since arithmetic encipherment is so strong by itself, it takes very little extra to push it up to a 10 rating. I suggest using a general polyalphabetic cipher of period 4, that is, a substitution with 4 independent, well-mixed alphabets used in rotation. An arithmetic encipherment followed by a general polyalphabetic encipherment with a period of 4 or higher is rated 10. It leaves an opponent with nothing to go on, no letter frequencies, no contact frequencies, and no way to utilize a probable word.